Hey, come here. Did you know there are only 4 types of loads that every structural engineer needs to understand? Just 4. And once you know them, you can design any structure, from a simple beam to a massive bridge, with confidence. So what are they? Axial, shear, bending, and torsion. Sounds simple, right? Well, not quite. These forces don't just act alone. They interact, overlap, and completely change how your structure behaves. Let's break them down one by one and see how they really shape the way we design. Let's start with axial forces. They're the straight push or pull forces that travel along a member's length. You can think of them in 2 directions, tension and compression. In tension, a member is being stretched apart. Steel loves this kind of work. It's strong, predictable, and efficient. But as it stretches, it also elongates. How much it stretches depends on the force, its length, the cross-sectional area, and the stiffness of the material. That's why, in structures like suspension bridges, the cables take on that smooth parabolic curve. They're following the path of pure tension, the most efficient way to carry the load. Now, compression sounds just like the opposite, push instead of pull. But compression brings its own problem, buckling. If a column is short and stocky, it can handle the load easily. But make it long and slender, and it can suddenly bend and fail, even under a smaller force. So when designing compression members, you don't just look at the material strength. You also check the slenderness ratio, because sometimes your column won't crush, it'll buckle. Now, let's move to bending forces. Imagine a beam resting on 2 supports with a load in the middle. It bends downward. The top fibers get shorter and the bottom ones get longer. That means the top is in compression and the bottom is in tension. This difference between top and bottom is what we call bending. In steel, this isn't a big issue. It can handle both tension and compression. But in concrete, it's crucial. Concrete is great in compression, but terrible in tension. So we reinforce the tension side with steel bars to prevent cracking. In post-tension slabs, we even place tendons near that tension face. They pull it tight, keeping the concrete compressed and safe from cracks. Understanding where the tension and compression zones are helps us make every beam lighter, stronger, and more efficient. Then comes shear. When a beam carries load, that vertical force has to travel down to the supports, and it doesn't go straight. It moves diagonally, forming a kind of internal truss made of compression and tension zones. This diagonal force flow is what we call shear. You can even see its effects. Those diagonal cracks that appear near the supports of reinforced concrete beams, that's shear at work, trying to tear the beam apart. To stop that, we use stirrups, vertical steel bars that tie those cracks together and keep the structure from failing suddenly. Because shear failure is brittle, it doesn't give you much warning. Everything seems fine until it's not. Finally, torsion, the twist. Whenever a load is applied off-center, the structure wants to rotate. You see this in cantilevered beams or when part of a structure sticks out with no direct support. Torsion causes the beam to twist along its axis. And while some torsion can be relieved through other load paths, primary torsion, the kind that's essential to stability, must be resisted directly. The problem? Torsion interacts with bending and shear, making reinforcement design much more complex. That's why engineers usually try to avoid torsion altogether by aligning loads better or adjusting the geometry. Every structure you design, every bridge, tower, or slab, is a balance between these 4 forces. Axial keeps things straight and strong, bending shapes the curves, shear transfers the load, and torsion handles the twist. Together, they create the dance of stability that holds our world up. So next time you look at a building or a bridge, remember, it's not just concrete and steel. It's a story of tension, compression, bending, shear, and twist, all working together to keep everything standing tall. If you enjoyed this, make sure to like, subscribe, and share it with your fellow engineers. Keep learning, keep building, and I'll see you in the next one.